Hi, my name is Javier Akira Luca de Tena. I'm a software engineer at Line since 2017, and today I'm going to talk about traffic-intensive storages at Line messaging application. These are the topics we are covering today. We will start with a brief introduction to our messaging application. Then we will talk about the storage requirements needed for it and how to achieve those requirements with Apache HBase. Here we will go through the process of improving our clusters and how important it is to model the data correctly. So, Line messaging application has around 200 million active users and around 4 billion messages are sent every day. It's not only a messaging application, you can think of it more like a platform with many other family services. But today I will be focusing only on messaging. Let me introduce you to the basic business logic of Line messaging service. Every user action will generate a series of events, and events are something that is used by the client application to update its state. So for example, user A sends a message to user B, then this action will generate some events indicating that user B has received a message. Then user B will open the chat, read the message, and this again will generate more events indicating to user A that the message has been read. This does not only apply to messages. For example, when a user updates its profile picture, an event will be delivered to its contact so they can update with the user B new profile picture. So it's basically a big synchronization service. This is a simplified version of our backend. The request from the client application will go through our in-house API gateway and reverse proxy called Leggy, and Leggy will redirect the request to the corresponding backend. Then the backend will make use of our storages to satisfy the request. Sometimes when we need to process something heavier in the background or retry some task, that is done with the asynchronous task processor. So this way we can relieve the application backend load a little bit. And in general, the backend is very heavy in storage usage. And today I would like to focus on these two, Redis and Apache HBase. Redis is fairly well known by many engineers. It's an in-memory data structure store, and we use it as a database and as a cache. Then we have Apache HBase, which is a distributed key-values store that provides random real-time read-write access on top of HDFS, which is the Hadoop distributed file system. And it's our persistent layer. These two storages have data for messages, events, user data, social graph, and well, much more. So let's talk a little bit more about Redis. We actually have two flavors of Redis cluster. First, we have our in-house sharded cluster. This was developed internally by Line when the Redis official cluster was not released yet. Here, data is split in shards that are replicated in a master-slave manner. The location of each shard is stored in Zookeeper, so the Line Redis client just needs to synchronize the shard information with Zookeeper in order to locate where the shards are located. Then it can directly communicate with the shards to write and read data. The cluster manager server updates the shard info in Zookeeper and also checks if the cluster is healthy. We are also slowly adopting the Redis official cluster. It has built-in shards that are replicated in a master-slave manner, and it uses something called gossip protocol, which is used to propagate information about the nodes across the cluster. And then we have Apache HBase. This could look a little bit more intimidating, but it's actually not that complicated. Data is organized in tables, and tables split their data into regions. And you can consider the regions such as like data split or shards. Each region is served by a region server, the blue thing that you see here. And they handle writes and reads for the regions by accessing the Hadoop distributed file system to write and read data from disk. Then we have the master process, which is used to administrate the cluster and control the aliveness of each node. And finally, we have Zookeeper, which is used to store configuration and coordinate tasks within the cluster. Now, HBase clients will communicate first with Zookeeper to know the information about the cluster and the location of a table called meta, which has all the information about the rest of the regions in the cluster. Then once the HBase client reads this meta table, it knows where to locate the regions, and now it can communicate directly with the region server to write and read data. So we said the region server makes use of the Hadoop distributed file system. And here data is divided in data blocks that are served by data nodes. Each block is replicated a configured number of times in different data nodes, and the name node will have the information about where to locate each block, and it will make sure that the amount of block replicas is kept so we don't lose data. Okay, so now we have a general idea about our service and our storages. Let's talk about the requirements. We need to support around 2.7 trillion requests every day, having 3 times the usual traffic at peak during the New Year's greetings. And this means around more than 100 million requests per second. And we also serve around 1.6 petabytes of data only for service. This is not including data for analytics or metrics data. And our storages are directly related to what our users will be experiencing. And requirements have the purpose to satisfy user needs and offer the best possible experience. Storages need to be performant and reliable, so the service always behaves as expected. It needs to be highly available, so for example, a common hardware failure does not affect end users. And of course, we need to offer a consistent view over our data. We don't want any user to see old or wrong data, right? But we also need to keep our systems maintainable and scalable to avoid any unnecessary cost. So let's go through the requirements more in detail. One requirement is that our storages need to be maintainable and scalable. Here is where the in-house Redis cluster struggles the most because it cannot be dynamically resized. This will also make very difficult to upgrade the Redis version, and it also has very high operational cost because every time we want to expand the cluster, we need to create a new cluster and migrate the data in the background. This takes lots of time and it has a high operational cost. The Redis official cluster addresses some of these problems and can be dynamically resized. But a few years ago, when we tested along with Redis 3, we experienced a performance drop as we had new nodes while the memory and network consumption went up. So we are willing to try newer versions of the Redis official cluster and see how it has evolved. Finally, we have Apache HBase, and I think here is where Apache HBase shines the most, since it has horizontal scalability without any performance degradation. We can also roll and upgrade versions, and we have put some efforts on building automatic tools, so it's quite easy to operate. And well, in general, I think you will agree with me that cost of memory is higher than cost of disk. Another important requirement is that our storages need to be highly available and fault tolerant. Our backend is a more traditional Java multi-thread application, so when a storage is experiencing some problems, it will make threads wait. And this could have a negative effect on the service and could also affect our backend reliability. This is especially noticeable in critical places with lots of requests. To solve this, in general, we try to keep Redis and HBase client with short request timeouts, and we try to keep the cluster recovery time at its minimum. But sometimes that is not enough. For Redis, what we have is we implemented a short circuit breaker mechanism. So when the response time increases, we temporarily mark the Redis shard as failed and stop sending requests to it. This is quite important because Redis is single-threaded, so if it becomes slow, it will affect other requests going to the same shard. For HBase, what we did is dualize the cluster. We built 2 identical clusters, and we send the request to both clusters, ensuring that at least one succeeds. In case one fails, the request won't be blocked, and we also get the benefit of being highly available. But now we have two identical clusters with same data. We have the risks of occasional temporary inconsistency, so we can only use this when the data is either immutable or in places where we can tolerate some amount of temporary inconsistencies. So it cannot be used everywhere. Another requirement is to offer a consistent view over our data because we don't want the users to see wrong all information. In general, we want to use Redis as a cache, but in the early days of line messaging, our data was completely stored in memory using Redis, and we kept using it and scaling it out to handle the increasing traffic and the increasing number of active users. Over time, this has become a big cost due to the amount of memory that is needed. What's more, even having data replicated in a master-slave mode, we were afraid of losing data due to having everything in memory. So we decided to write data also in HBase. But to not have any performance impact at the time, we decided to write HBase asynchronously with an offline retry mechanism. But as you may have noticed, there are no real transactions between Redis and HBase. And also by writing data asynchronously, we are more prone to suffer from race conditions. So keeping both storages consistent over time is very challenging, and we were in a state where we cannot 100% trust the data that is being stored in HBase. And well, with this, we have not solved the problem, the memory problem. We still have to write everything in memory using Redis, which is quite expensive. So we decided to make HBase the primary storage for most of our core features and change Redis' role to use it as a cache, like a more traditional application architecture. This way, we will have a single source of truth that we can trust, and we can reduce the memory usage. We also prevent potential data loss thanks to HBase persistence and HDFS data replication. So HBase becomes the primary storage for most of our core features, and also new features are built on top of HBase. And not only that, HBase has started to be used in new services and modules. We cannot forget about Redis, because still it's going to serve most of our reads, but it's clear that HBase responsibility and usage has been increasing. This means that HBase has a bigger impact on the user experience, and we need to take HBase requirements very seriously. So we said that with HBase we can achieve horizontal scalability, reduce the cost by reducing memory usage. We have better data consistency and reduce the risk of data loss by making HBase primary. And we can achieve high availability thanks to dualizing the cluster. But what about reliability and performance, especially if we compare it to an in-memory storage like Redis? We need to make our clusters more reliable and performant, and we do that by evaluating and testing carefully every version, settings, or feature that we plan to use. Also, as any other technology, performance is going to depend on how we use it. So we need to be careful about how we model and access our data. So let's see how we achieve those requirements with Apache HBase. And to make, as I said, to make our cluster stronger, we evaluate and test carefully every new version, feature, and settings. So let's see how that's done. So we believe that the open source community is doing an incredible job with Hadoop and HBase, but as any other piece of software, it has bugs. The question is, are those bugs going to affect our service? So in order to avoid any possible bug or performance regression to be introduced into our service, we go through an evaluation and testing process. In order to do that, we have built a testing environment that replicates a very similar conditions and traffic to what we have in our production clusters. We do that by intercepting the request the application backend makes to the production HBase cluster, serialize the request, send it to Kafka, then we replay those requests with a small consumer into our testing HBase cluster. Then we can try new versions or features, see if we have some bugs or any performance regression in a safe environment with almost identical traffic as production. And this is our usual flow. We start by replaying the requests. We deploy the new version or feature that we plan to test. We detect and fix bugs, or maybe we backport the fix from if the open source community has already fixed it. And if we have a chance, we contribute back to the open source community. And we finally safely apply to production. So let me talk a little bit about some of our recent works using this testing environment. We try to improve our cluster's reliability by reducing performance spikes that are caused by disk slowness, because, well, disk is usually more unpredictable than memory access. And also spikes caused by latency increase, because sometimes networks could be occasionally unstable. These issues can be mitigated with a feature called head reads. So what are head reads? Well, when HBase makes use of the data node to read data and the data node tries to read data from disk, many things can happen. The network could become punctually slow, or we could have a slow disk because some hardware issue or because some punctual I/O increase because it's doing some heavy operation. In those cases, with head reads, HBase region server will try to request some data from the same data from other data nodes. This is possible because, as I said earlier, its data block is replicated into multiple data nodes. But now, how do we test this? In normal conditions, we are not going to have any flaky disk or any latency issue. We need to simulate those scenarios, and we choose to use something called LD preload. This tells the unique dynamic linker to load your code before any other library. So we made this small C code that injects a small sleep before the actual read to disk happen. This way, we were able to reproduce flaky disks, and we could start seeing like 1, 2, 3 seconds load response times. So after reproducing a slow disk, we turned on head reads, and, well, response time spikes disappeared. We were successfully testing head reads, and, well, they seem very useful. However, after a few days of usage, we observed that suddenly the thread that handles the HBase request went busy and did not decrease at any point, making the user unable to process more requests. What was going on? So we took the thread dump and we observed that HBase was acquiring some kind of lock, and the head read part was stuck trying to take something from a blocking queue. So after reading the code and debugging, we found out what was going on. HBase was acquiring some read lock. Then it submits a read task to the data node, but because the data node had some issues or it just died, there was no actual result coming from the data node. Then the blocking queue that has the read results was blocked, waiting for a result that will never come. Then HBase read lock was never released because the read was stuck there. So requests were stuck waiting for the read lock to be released. So after all this investigation, we realized that actually the open source community already fixed this issue. So we backported it to our internal Hadoop branch, and we never saw this error again. We took the chance and reported this locking issue to the HBase open source community, and along the way, we also fixed and added new head read metrics. So by using this technique of replaying requests in our test environment and evaluate features and versions, we have made our clusters very strong, and we have actually contributed multiple times to the open source community. Now, our clusters are very strong and reliable. Are we ready yet? Well, no. Cluster might be fast and reliable, but we could still see some bad performance. Like any other technology, it depends on how you use it, and HBase is not an exception. the table schema design, how you model your data, how you access your data, is going to play an important role. So to make a good data schema design, we need to understand how HBase works internally. So let's see how important is having a good table schema. But before that, as I said, we need to understand a little bit better how HBase works internally. So let's see how data is organized in HBase. Data is organized in rows, and rows have keys and values like any other key value store. And each row key will have multiple columns, which are grouped into column families, and each column can have multiple values. Now, the important thing here is that data is stored in cells, and cells are versioned and immutable. So every time we update a value, we are actually just adding a new cell with a new value and a new version. And since most of the time we are just reading the latest version, it will give us an impression that we have updated the value. When we write data in HBase, we don't write directly into disk. We write first into an in-memory store called the memstore, and once in a while we flash the memstore into disk, into an immutable file in the Hadoop distributed file system called hfile. After a while, since hfiles are immutable, we may have flashed memstore many times, we could end up having multiple hfiles. What HBase does is it compacts them in the background into fewer files. And here a very important detail is that I want you to remember, because it's very important to understand the rest of this session, is that in both memstore and the hfiles, cells are sorted by row key, column, and version to easily locate the data. And as you may have guessed, when we read data from HBase, we need to read from both stores, memstore and hfiles, and merge the results. So now that we have some knowledge about how HBase works internally, let's have a look at the study case. We have a table that stores a list of message IDs per chat. This table is used to calculate the amount of our read and read messages, and also mark the messages as read. So imagine user A has message ID 7 and 11 and read, being 11 the latest message in the chat. Then user A opens the chat and read the messages from 7 to 11. After that, we update the number of unread messages for user A, and we mark the messages as read for user B. In order to do that, we need to scan messages IDs by range, considering that messages IDs in line messaging application are numerical and globally incremented. So our first approach was to store the message IDs list by chat in a single row. We use the user IDs of both users, the participants of the chat, to build the row key to identify the chat. User IDs are numerical, so we use the one with the lower numerical value and hash it, so we can distribute rows across different nodes in the cluster. Then we place the message ID as the column names and also as the version. Then we place the message IDs as the column names and also as the version. So we can easily do a range scan over the versions. So for example, what we will do is scan from version 123 to version 245. The reason why we did not use the column for the range scan is because most of the time users will be reading recent data, which means the scan can be satisfied by reading only the memstore or the most recent hfiles. So by doing the range scan over the version, we can avoid to read older hfiles, and this will save us some I/O and make better usage of our caches. We also store which user ID is the sender of the message as the cell value. So after we deploy this stable schema in production, we observe that some serious performance spikes. This could have a negative impact in the user experience, so we need to fix this. But we have one hint, and is that when HBase flushes the memstore into disk, the performance spikes disappear. So our issue is probably going to be in the memstore. So to understand what was going on, let's see how the memstore works internally. We said the memstore is an in-memory sorted store, and we can potentially implement that with a simple sorted linked list. However, that won't be very efficient because we will need to traverse the list sequentially until we find the element we want, which has time complexity n. So HBase implements the memstore as a skip list. So what the skip list does is it creates linked list on top of the original sorted linked list. You can consider this new linked list like fast lanes. Then we can quickly locate our data with time complexity log n, which is, well, way more scalable. We can easily translate this into our memstore, which stores cells sorted by, again, row key, column, and version. So let's go back to our message ID list table. And here we have our memstore, which is a skip list, as we said. We have the data sorted by row key, column, and version. We have a column for each message ID, and we have the message ID also stored as the version. So we want to scan the message ID list for the chat between user 333 and user 555. So first, we locate the row key of our chat, so we seek into the memstore to the beginning of the row. Since it's a skip list, the time complexity is log n, as we just said. Once we located our row, we will go ahead and check the first column and its version. But it does not have the version we want. We are looking for versions between 100, 1000, and 1010. So the memstore will say, hey, go seek next column, maybe you have more luck there. And we thought the memstore will just go ahead and check the next element in the skip list. But the reality was that it was traversing the whole skip list each time we wanted to seek to the next column, which is again time complexity log n. This was because of the implementation used by HBase, which was the Java concurrent skip list map. And well, I don't want to go too much into implementation details, but this will call a method called tailmap that creates an immutable internal sublist. And in order to iterate over it, it needs to traverse the original skip list again. So we are checking each cell until the memstore. So we are checking each cell in the memstore until we find the columns with the versions that we are looking for, again from 1000 to 1010. So we are seeking to the next column many times. And as we said, the time complexity is log n every time the memstore tells us to seek to the next column. Now imagine we need to filter out many columns. Let's say m number of columns and much more than 1000 columns. We will end up having time complexity of m log n, and that was the reason why we had such a bad performance. We tried to fix the memstore behavior, but because of other trade-offs, it was never merged. But the patch is available for everyone if you want to check it out. So as I said before, the spikes disappear when data is flushed from the memstore to disk. And some of you might be wondering why. So, well, let's see why. When we read data from the disk, from the H file, we first load the data block from disk, and HBase internally uses a byte buffer for the purpose. So when we want to seek to the column we are looking for, HBase will start from the beginning of the byte buffer. And it will sequentially traverse the byte buffer until it finds the data we are looking for. This has time complexity n, which is, well, not that good, but it's better than mlog_n that we were experiencing with the memstore. Now, going back to our message ID list schema, it's clear that having the message ID as the version is not the best idea. What we did was move the message ID to the row key. So now, instead of having one row key with the whole message ID list in it, we have the message ID list distributed in multiple rows. And what we do is arrange query over the rows instead of over the version. Now, memstore can seek directly to the row which has the message IDs we are looking for. So we only seek once, which is just time complexity log n, and well, problem solved. So let me wrap up this session. We started talking about our requirements, or storage requirements, and how important they are to offer the best possible service to our users while avoiding unnecessary cost. So our storages need to be performant, reliable, highly available, and scalable, and we need to offer a consistent view over our data. Some of these requirements are satisfied by making HBase the primary storage, but we still need to make our clusters more reliable and performant. We do that by testing and evaluating every version and feature carefully in a safe testing environment that replicates conditions and traffic very similar to production. Also, to extract the performance out of HBase, it's very important to design a good data schema, and to do that, it's very important to understand the technology internals. And this not only applies to HBase and Hadoop, I believe it applies to any other technology. So before I finish this session, let me talk a little bit about some of our future challenges. One of them is that we need to overcome some of the key value storage limitations. We need better transactions and features like secondary indexes. We also need to improve our multi-data center architecture. Currently, we have our backends and storages deployed in 2 data centers for disaster recovery purposes. But most of the time, some of these machines are underutilized because we need to assume that the whole traffic can be handled by any of the data center by itself, so we need to increase the resources. Also, the current messaging application business logic assumes that data is most of the time consistent everywhere and every time. And well, HBase can replicate data over different data centers, but it's done asynchronously, which suffers from eventual consistency. We also cannot forget about the existing latency between data centers, because they are placed in different geographical places, and there is a physical latency between them that cannot be avoided. So that is going to make things even more difficult. So considering that there are projects or places that does not have such high performance requirements, and some extra latency could be potentially correlated, we have been considering and exploring other storages and solutions that can potentially offer consistent view over our data across multiple data centers. So, well, let's see how we can transform our storages in the future to offer an even better service. Thank you.